Alright, here we go with section 7 in chapter 9. This is about special functions. So we've kind of finished up with quadratics, and we've learned a lot about them, and now we're going to take what we've learned about quadratics and apply it to a couple of new functions. So lots of vocab and lots of kind of cool looking things, but not a lot of actual problems. First, piecewise linear function. The name says it all. It is a whole bunch of pieces of straight lines that combine together to make a function. So any graph that's made up of multiple sections of line segments. Okay, piecewise linear function. So a bunch of pieces that are all straight lines that combine together to give you a function. One example of a piecewise linear function is called the greatest integer functions. This is a general category here. This is a specific example here. I like to call it the round down function. That's how I remember it. So it's a series of line segments such that the output or y value is obtained by rounding the input value down to the nearest whole number. So let me make a little t-table just to show you what I mean. If x is 1.1, what is the output? 1. If x is 2.6, what is the output? 2. So the output is always an integer. So your graph is going to be a bunch of flat horizontal lines. Because if I put an input of 1.1 or 1.2 or 1.3 or 1.4, the output stays as a 1. In fact, let me zoom ahead to the graph. Here's what the graph looks like. So don't copy this down yet. We'll get to this slide soon. But basically, if you input anything between 0 and 1, you round down and you get 0. But anything, as soon as you put in a 1 stays as a 1, and then anything from a 1 to a 2 rounds down to just be a 1. Anything from 2 to 3 rounds down to 2, etc., all the way forever. So this is called the step function, because it's like a staircase up, up, up. Alright, another one is the absolute value function. This one we've already learned about in terms of equations and solving mathematically, but not in terms of graphing. So we'll start to learn about how the graph relates to the function and the solutions that we got earlier in the year. So this is a piecewise linear function. Again, piecewise means it's a whole bunch of pieces of straight lines, and it's a function. And it always has a positive output value from the absolute value part, just like we learned before. So piecewise linear function is a whole bunch of pieces of straight lines. Then you can just have a generic piecewise defined function. And this is a whole bunch of pieces, but they don't necessarily have to be linear. So it could be a whole bunch of sections of different graphs all stitched together, and each of those sections could be a parabola, could be a straight line, could be an exponential function, could be anything like that. And very last, because this section is all about domain and range, I just want to remind you, domain is the set of all possible inputs and outputs. Sorry, I said that wrong. Domain is the set of all possible inputs, and then range is the set, again a reminder, set of all possible outputs. Okay, so a lot of these questions will give you maybe a piecewise defined function and ask you what is the domain, what is the range. Okay, as I just showed you on the previous slide when I was giving the definitions, this is the greatest integer function, aka the round down function. The symbol for it is typically a double bracket, although this image that I found online had just a single bracket, so perhaps either one of those could mean the round down function. And as we described, you just take whatever the input value was, the x-coordinate, and you round it down, and then you plot that point, and it ends up leading you to a bunch of steps like this. So it's called the step function, like a staircase. The other is the absolute value function. So we've spent a lot of time solving problems with absolute values and branching to get to solutions, but we never actually looked at what the graph looks like, and we never defined it in a way like this. Or at least I don't think we did. So this is called a multi-defined function, aka a piecewise defined function. So that means each different piece is going to be defined separately. So absolute value, you can see it's got two sections, the left side and the right side. And the way that it works is you give the function its symbol or name or equation, and then you define it separately for the different domains. So the output value of the function is x, which is the same as the input, which means you didn't change anything whenever x is greater than 0. Now think about absolute value. That makes sense, right? If you input a positive number, you just keep the number the same. So anytime x is bigger than 0, the output is just x. So we plot the function y equals x right over here. Anytime x is bigger than 0, we're looking here. And then if x were negative, we need to change the sign. How do you change the sign of something? Well, you multiply it by -1. So when x is negative, which is over here on this side of the domain, the output has to be -x. And a negative of a negative makes a positive, so this line right here has positive values even though the equation is y equals -x. So this is the general shape of the absolute value. It's also called a v function because it looks like a v. And both of these two functions, just like lines and parabolas that we learned about before, they can all be transformed. So we learned how to shift left and right, up and down. We learned how to reflect, and we learned how to dilate. You can take this exact shape and slide it left or right or up or down and then plop it back down, and it will maintain its shape while changing its location. Or you can keep its location the same and reflect it or dilate it, or any combination of those. So both of these base functions or parent functions can have a whole bunch of changes done to them. Alright, last little bit. I talked about piecewise functions here with the absolute value function, but in general you can define any amount of sections. So you write the function like this: f of x equals, and then you put all the different, so here would be a specific equation like 2x plus 5 or x squared minus 3 or something. So you put in the specific function that you want to use, and then you put a comma, and then you put the domain or the location of where you want to use that. And you can have an unlimited number of sections. It could be just 2 pieces, it could be 3 pieces, it could be 50 pieces. It doesn't really matter. And so you stitch all these pieces together. You need to make sure that your domains don't overlap, because if they overlap, then you won't pass the vertical line test and you won't be a function. Alright, let's do some examples. First one here, this double bracket is the round down function. And so you could try to figure out the inputs and the outputs, but a much easier way is to look at this and say, we learned that when you change x into x plus 1, this means we went left 1. Okay, so we know the original function, there is a line here and here and here and here. We just take this original little piece and we move it left 1. So it's open here, closed here. And then from there I just plot this function because you've hopefully memorized the shape. It's like a staircase, right? So as long as you understand that the first piece moved left 1, again, let me show you what it looked like. It was like this, right? The little line segment from 0 to 1. So if we move left 1, we go from -1 to 0, and then we can just go from there to get the entire rest of the function. How about this one? This one says we have stretched by a factor of 2. Okay, so we haven't slid at all, so our first one still starts here. Its height was 0. Well, if its height is 0 and you stretch by a factor of 2, its height is still 0. The next one was up 1, but we're stretching by a factor of 2, so instead I need to go up 2. Solid dot, open dot, up 2. Solid dot, open dot. And then over here, down 2. Solid dot, open dot, down 2. Solid dot, open dot. So this function is vertically stretched out by a factor of 2. Okay, so these are examples of shifting or stretching the step function. And then now we have an absolute value function. So what does this mean right here? This means down by 3. So the normal function, let me go back to it again. It's a v. Absolute value function is a v with a straight line with a slope of 1 and -1 starting at the origin. So if I'm going to move, this is my base function, and I'm going to move it down 3. I just start at the origin and I go down 3, and then I draw in my function, which it was a v. So I draw the same v with slope 1 and slope -1. And there we go. Now I want to tie this quickly back into the things we learned before. There are 2 solutions, 2 intercepts. Here's one here and here's one here. One's at +3, one's at -3. So if we look at this equation, if we set the output or y value to 0, and we said 0 equals absolute value of x minus 3, and we solve, we would do +3 plus 3. We'd get 3 equals absolute value of x, and we would branch, or you'd write x equals plus or minus 3, because absolute value has two solutions, and this is exactly why. So you can now start to understand how the math that we did earlier relates back to this graph that we're doing now. Okay, just 2 more examples and then we're finished. Here we've got a piecewise defined function that's broken into 2 pieces. I'm going to use the equation y equals -x plus 4 anytime x is smaller than 1, so on the left side, and I'm going to use x minus 2 anytime x is bigger than 1. So the first thing I'm going to do is I'm going to draw a dotted line to separate my coordinate plane into the left and the right. Okay, and I'm going to label on this side over here I'm using -x plus 4, and on this side over here I'm using x minus 2, right? Because x is larger than 1 over here, and I'm using x minus 2. And all I'm really doing is I'm taking these two lines and I'm stitching them together on this one graph. So let's plot the equation negative x plus 4. So my intercept, here's my origin, so 1, 2, 3, 4. My slope is negative 1, so down 1 over 1, and up 1, backward 1. So this is my line here. And I would have kept going, right? I would have kept going with these dots. But this domain part restricts me and says only when x is less than 1. So I stop my line right here. And now on this side, I plot x minus 2. So let's plot this line. So we have a starting value of negative 2. My slope up 1 over 1. Up 1 over 1, etc. all the way through. So this one I'm going to start right here, but it says just greater than, not greater than or equal to. So this has to be an open circle. And then I connect in my line. Okay, so it looks kind of weird. It's a disconnected two pieces. But still, the domain is all real numbers, because if I put in a number less than 1, I'm going to use this segment. If I put in a number bigger than 1, I'm going to use this segment. And any input value is acceptable, and I'll get a different range of outputs because of that. So this is called a piecewise defined function. You stitch together sections of different graphs. Okay, our very last example here is going to be an absolute value one. When I want to look at this one and graph it, I can see right away it's been moved down 3. But the part inside the parentheses is multiplied. It's got a 2 in the front. So let's factor out a 2 here, leaving behind x plus 2 and then minus 3. So here, this one means down 3. Okay. This one here, what does that mean? Think about it. X plus 2 means left by 2. And then this means, let me label these guys. This guy means stretch by a factor of 2. So first, we know that the vertex of the V-shaped absolute value function normally starts at the origin, but I'm going to go left 2 and down 3. So left 2, down 3. So now I'm going to start right here. Normally, my V has a slope of 1 over 1 up 1, but because this factor of 2 right here, I'm actually going to go over 1 up 2, over 1 up 2, over 1 up 2, over 1 up 2. So my slope is doubled, and I can draw it in like this, and then likewise the other side. So it's kind of like a parabola in that it goes up on both sides, but it's kind of like a straight line in that the two segments are linear and not parabolic shaped. Okay, so I've got my quadratic like this, and you can look at the graph and you can see where your two solutions would be if you tried to find the y-intercepts. And you could even set this equal to 0 and solve, and you'd see that I got negative 1/2 and looks like negative 3/2 as the two solutions. So you can make all these kind of graphs by thinking them as shifting the original graph up, down, left, right, stretching it, shrinking it, and reflecting it. Alright, that's it for this section. You've taken your knowledge of quadratics and translations and applied it to two new functions, the step function and the absolute value function, and then you've seen how the absolute value function can be written as a multi-defined function or a piecewise defined function with more than one piece stitched together. Alright, I'll see you in class.